Welcome everyone. Thanks for coming out tonight in the traffic here in Atlanta. Tonight I'm going to talk about a topic that was in my now 2 books ago, Software Architecture Fundamentals. One of the things that Mark and I, when we wrote that book, wanted to do was there's a lot of baggage in the software architecture world, and I'll give you a great example of that. Does anybody know where the phrase non-functional requirements originates? A lot of people refer to what we call architecture characteristics as non-functional requirements. Do you know where that name comes from? You've been using it forever, right? Where does it, exactly. Non-functional requirement, but where does it come from? How many people here, you're gonna expose something about yourself demographically if you answer this question in the affirmative. How many people here remember function point analysis? That's where non-functional requirements came from because they weren't function points. They were non-function points. And we've been using that term even though we stopped doing function point analysis like 30 years ago. We've still been using that term non-functional requirements because it just kind of stuck. So that's one of the things that we were trying to do was, can we get away from some of the baggage in the software architecture world and rethink it as if it were kind of a new thing? And this is a good example of, I'm a big fan of iterative software development and iterative design and architecture. And Mark and I iterate on our material when we write a book as well. Because when we first had the crazy idea to write a book about software architecture, we realized, I have no idea what would be in that book because there's just so much stuff that could be in that book. But what we did was started putting material together and then teaching it at workshops and conferences and started iterating on the material. And one of the outcomes of that iteration is the distinction I'm making tonight between architecture styles versus patterns. I'm primarily going to talk about architecture styles tonight. And Mark and I and Raju Gandhi, who some of you know, are currently working on head-first software architecture, which, as you know, is almost like writing a graphic novel, and we've been forced to rethink the metaphors around this as well, so I have some new metaphors to try it on you about this distinction. But we used to call all these things patterns, things like microservices and microkernel and layered architecture, but then we realized at some point there's a distinction to be made between a style versus a pattern. A style in architecture is a named topology. It's an organization of components and parts, usually including how they communicate with each other and how they access data, etc. And you can really only have one style per system. Now, there are lots of hybrids, but every one of them has one dominant style, whereas a pattern is some solution, contextual solution to a problem that can be used within any architecture style. Communication patterns are good examples of that, like events. Events can be used in event-driven architectures or microservices or service-based architectures or enterprise service orchestration-driven architectures. And so eventing is a pattern, but microservices is a style. So the head-first version of this was we're using the metaphor of clothing. The clothing is the style, like a shirt or trousers, but the pattern are things like polka dots or check marks or something like that. And notice you can apply any pattern to any one of the styles, but the style says something structural about it. So let's talk about some styles, and I'll give you some distinctions with some patterns to show you the distinction between styles and patterns. And the first of these I want to talk about is the simplest one, and it's the default architecture in many organizations, this idea of a layered architecture, because it mimics the kind of model view controller thinking about the world, with a presentation layer, and a business layer, and persistence layer, and some sort of data access layer. And one of the things that's important to understand about all these styles is understanding the philosophy behind that style, because that's what allows you to bend it without breaking it. If you don't understand the philosophy and you start making random changes, you can do serious damage and in fact not get the benefit that you were trying to achieve by choosing that style. And I'll show you an exact example of that within this layered architecture, because the main focus, the philosophy in this architecture is good separation of concerns. Because what we're limiting here is rippling side effects. If I need to change some business logic in this application, I can change it in the business layer, and the only two places I can possibly affect are the presentation layer and the persistence layer because they're the only ones immediately adjacent to that layer. And in fact, we say that in a layered architecture, each of these layers is closed, meaning that they only take requests from the layer above and flow things down to the layer below. And this gives us good separation of concerns so that we know that if we change the persistence layer, we know we're only possibly breaking two things. And that's the underlying philosophy of this layered architecture. But then you run into situations where maybe one of those layers is not useful for every request. Some requests you need to go through a particular layer, but in some requests you don't need to go through a layer, like for example a services layer. So I can get my fancy pointer to work here. There we go. There's an accelerometer in this thing. You have to figure out where it thinks the screen is, and then it'll figure it out later. Okay, it doesn't want to work, so I'll play with that later. Yeah, it'll show up on my screen and show up here too. But it's, okay, well, anyway, I'll just point to it directly without using my fancy pointer. The services layer here, this is a way to solve what's called the architecture sinkhole anti-pattern. What if some requests don't really need to go through that services layer, and it's just a waste of time? Maybe it goes through a data transformation and just kind of sinks through that layer. And so one of the ways you can fix that problem is create an open layer in a layered architecture like this. And that means that if I don't need anything from the services layer, I can just bypass that one and go directly from the business layer to the persistence layer. And that solves the architecture sinkhole anti-pattern. But, like everything in software architecture, creates a trade-off. Everything in the software architecture is a trade-off. And the trade-off I've undertaken here is I've started chipping away at the philosophy of this architecture, the separation of concerns. Because now, if I change the persistence layer, what might I break? I could break the services layer and the business layer down because more things are coupled to that persistence layer because I've created an open layer above it. This is a classic example of, well, which of these is the least worst? Because neither of them are perfect, and so now you've got to figure out what the trade-off is between those things. There are lots of variants and hybrids for this particular architecture style. The one on the far left is typically of desktop applications. We have a separate database, like a client-server application. The one in the middle is a typical web application with some sort of application server in the middle. And then the one on the right is something like an embedded application or mobile application or something like that. Now, as an architect, you're responsible for designing the architecture, but you're also often responsible for supervising the construction of that architecture. And what happens in the layered architecture if the reporting team comes to you one day and says, hey, it's taking our request too long to go through all those layers. We need to wire directly from the reporting presentation layer directly to the database and bypass all those layers. Is that okay? What do you think? Is this a minor compromise to my architecture? Or does this basically ruin the whole thing? Basically ruin the whole thing, because if you couple the database scheme and the presentation layer, it doesn't really matter what's in those middle layers. You can just set fire to those things because they're useless now, because a change in the database will have to flow up to the presentation layer. That's what leads you to not a layered architecture, but a big ball of mud. This is actually a technical diagram that I captured using a tool called X-ray of a real software system, where every dot is a class and the lines are the connections between the classes. So this is the bad version of when things get out of control. But what happens if you're in an organization where it's better to ask forgiveness than permission? What happens if the reporting team doesn't bother to ask you about this? They just do it. 6 months later, you find out, wait a minute, why is it? So governance is part of your job as a software architect as well. And I'm only going to touch very briefly on this because this is a deep subject unto itself. Maybe because my battery is dead here. This is a tool in the Java ecosystem, and here it goes, of course, going crazy. All right. This is a tool in the Java ecosystem called ArcUnit. This is based on JUnit, but is designed to help you govern the design of your architecture. Notice the first test here after the setup. No classes that reside in a package service should access classes that reside in a package controller. This allows you as an architect to codify some of your design in tests and then run these tests as part of a continuous build to make sure that the design that you wanted to be implemented is in fact being implemented and people are not cheating because they don't understand it or they're trying to get away from with something or something sneaky like that. This is really the topic of my book, Building Evolutionary Architectures, which just came out in second edition. This is automating architectural governance. And this is the Java version. And there's also a .NET version called NetArchTest, which gives you the same capabilities in the .NET ecosystem. So the drivers for the layered architecture are really simple to understand, really low cost. But there's one other thing that's worth mentioning about the layered architecture, and it's how it's partitioned. We partition things by technical capabilities in the layered architecture. Presentation, business rules, persistence, etc. Where do domain concepts like catalog checkout live in the layered architecture? Well, parts in the presentation layer, parts in business rules, and parts in persistence, and parts in the database. So we've kind of taken that domain concept and smeared it across all the layers in this architecture. This is what we call a technically partitioned architecture because we partition things around technical capabilities like presentation, business rules, etc. And this is very old school because since domain-driven design came out, we've mostly been focusing architectures around domain-centric designs, not technically centric designs. And we'll say more about that as we see a few more of these styles. One of the things that Mark and I wanted to do was to create a way to do a kind of an apples-to-apples comparison between these different architecture styles. And so we put together this star chart for each of the architecture styles in our book, where 5 stars is the best score and 1 is the worst score. And partitioning type here is technical. The number of quanta 1 here means this is a monolithic architecture, meaning it's typically deployed and implemented as a single big thing. Excuse me. Typically with a single big relational database as well. We picked a handful of desirable architecture characteristics here, deployability, elasticity, the ability to evolve, etc. And you can see here, the only one that's kind of confusing is cost. 5-star means good cost, which means low cost. And so we've realized after the fact we should make those dollar signs, and it should be a single dollar sign, not 5 stars, because good cost being low cost is kind of confusing. But otherwise, they all make sense. Layered architectures and monoliths in general are one of those that the bigger they get, the worse a lot of these architecture characteristics start showing up, like scalability and performance and elasticity. As they get bigger, it gets harder and harder to achieve those things. So let's look at another mostly monolithic architecture style, the microkernel architecture, which is also known as a plug-in architecture. And this one has 2 primary components. It's one of those architecture styles that once you've seen it, you start seeing it everywhere because it's so commonly used in tools and business applications, etc. The 2 primary components in microkernel are the core system, which is designed to change very little. It is the core functionality for the system, general business rules and logic, and no or as little custom processing as possible. The plugins are standalone independent modules which have separate business logic in them or the way you're updating the behavior of the application. And this is one of those that it's very much on a spectrum. So if you support plugins, you're not necessarily a microkernel, but if you're a microkernel, you definitely support plugins. For example, a browser is not a microkernel because it's perfectly functional with no plugins whatsoever. However, Eclipse is very much a microkernel architecture. Eclipse with no plugins, I think, can read and write text files, and that's it. Nothing else. Everything else comes in through plugins, which makes it such a flexible development environment. That was part of the original goal, was it can be a development environment for Java and C++ and a whole bunch of other stuff. But you see this in a lot of business applications as well. So for example, something like an insurance application that needs custom rules for different states. This allows you to create the kind of general processing for insurance claims in the core system and then customize all the little customizations for each state. This means you don't have to have all the states online to start going, just the core in 1 or 2 states, and you can get going and add them. Because generally, the plugins are completely stateless in regards to each other. They don't really know each other exist. They communicate only with the core system. In fact, things get ugly when you let the plugins start talking to one another like Eclipse does. More about that in just a second. The other use for this, and this is a great example of a microkernel, are things like linters, PMD, or source validation tools, because the tool itself will parse the Java source file and then apply rules to it and then spit out reports. Well, if there are no plugins, it's going to be boring because it's just going to parse the code and produce no reports. It's only by adding plugins do you actually make it useful. So this is a classic example of a pure microkernel, not just something that supports plugins. As I said, typically the plugins talk solely to the core system. Those are when these architectures work best and are least painful. You can have situations where the plugins talk to one another, a la Eclipse, but now, welcome to transitive dependency management. And as you know, if you've ever tried to install some plugins in Eclipse and they start fighting with one another about dependencies, etc., it gets very complicated because all that has to be resolved by the core system. In fact, they basically had to create OSGI to make Eclipse possible, because Java itself just did not have good enough modularity, because it turned out that, and this is true for the application servers too, pretty much everything you wanted to plug into Eclipse was using a different version of log4j. And you can't load the same log4j class file with 16 different versions in one JVM space, thus OSGI, which allowed you to do that, but it was notoriously a terrible leaky abstraction. One of the worst leaky abstractions ever used for production-like stuff. And so fortunately, we've mostly gotten away from that with Jigsaw and the ability to actually modularize Java itself now. But that's why OSGI came about, was to manage the dependencies and the craziness inside the Eclipse ecosystem. I'd be really curious to ask the Eclipse developers now, given what they know, would you have still gone the microkernel route? Because I don't know if you've ever tried to add something to Eclipse. It is complicated. You've got to understand a lot of moving parts to add something to Eclipse versus a lot of other plugin ecosystems which are a lot simpler. The drivers for microkernel are very much this modularity and simplicity. It's easy to understand this, but customizability doesn't really even show up on this list, but that's really the sweet spot here. The ability to customize stuff and basically freely plug things in. We actually have both adaptability and evolvability here. For us, adaptability is the ability to keep existing behavior and then add more onto it over time, whereas evolvability is fundamental shifting behavior over time, and this supports both of those things because a plugin can be A/B tested for its replacement and then gradually migrate to the next one and evolve away from it. The deployability is kind of cooked into this architecture, so it's easy to understand. This is the only architecture style that we called, from a partitioning standpoint, both domain and technical. Because when this is used for customizability, it's perfect. There couldn't be a better architecture style, which is why this shows up in a lot of customizable ecosystems. Enterprise service buses are basically microkernels. The BFF pattern, if you're familiar with that, the communication pattern in microservices is basically a microkernel. Every integration hub is a microkernel architecture. So you see this pattern all over the place where you have this ability of core behavior and then plug stuff into it to make it do interesting stuff. One of the problems that we have in the software world is not enough English words to talk about things as they change and evolve over time. And so let's talk about service-oriented architecture. Not to be confused with a service-based architecture or a microservice architecture. This is a service-oriented architecture. And yes, I know those are just different combinations of the same words, but that's kind of where we are here. We actually call this in our book orchestration-driven service-oriented architecture. And this was all the rage about 10 or 15 years ago. Consultants used to make a lot of money talking about how wonderful this orchestration-driven SOA was. So remember the layered architecture where we had technical layer and business rules and persistence, etc. This architecture basically said, here, hold my beer and watch this. You think you're technically partitioned, you haven't seen anything yet. The idea behind this architecture was this really strict taxonomy. And it was this kind of theory about how software works within an organization that was kind of encapsulated inside this orchestration-driven architecture. This was meant to be enterprise scope. So this occurred at about the time that a lot of companies were gathering together and turning into enterprises. And one of the things they were frustrated about was, okay, we used to have this idea of a customer, and then we merged with this other company, and they have a different view of customer, so we had to rethink it. We got all that fixed, and then we merged with another company that had a completely different view of customer. We had to fix it, and we're tired of fixing it over and over again. And so we need some solution to that problem. And so the solution to that problem was this idea of a service taxonomy. And so the service taxonomy in this architecture said that this top layer, business services, should be completely abstract, basically interfaces that describe what we do as an organization, like execute trade or something like that. No implementation details, in fact, no code. These are all purely just abstract functionality of our organization as a business. If there's no code here, if this is all just interfaces, there's got to be code somewhere. And that's what this layer was, these enterprise service layers. And these were at a different level of granularity than the business services up top. Because what these were supposed to be are these little magic Lego blocks that encapsulate some perfect little slice of business functionality. And the idea was anytime you have some new abstract problem at the top, you can just take a bunch of these little enterprise services and wire them together using this message bus thing in the middle. And then eventually there will come a day when we'll have all the enterprise services written and they'll be perfect. And we can stop writing code at that level, and all new application development can just happen at the message bus level and above, and we'll have reached enterprise nirvana as far as software is concerned. That's, of course, impossibly naive, but that's kind of the idea behind this taxonomy, that even transactionality, so the proponents of this architecture style believe that the transactional characteristic of these things was a completely separate role from the people who wrote them. So they actually had a job in these architectures for the transactionality manager who would edit XML files to figure out where transactional boundaries were between all these little Legos that just strung together to do stuff. We'll talk about why this is a terrible idea in just a second. There were some things that were not meant to be super reusable, application level services, so one-offs or very specialized things for certain applications. Infrastructure services, which is monitoring and logging and that kind of stuff. But then that enterprise service bus thing in the middle handled integration. This is where you integrated all the different pieces of your ecosystem together. It had a orchestration engine. That was the thing where you defined the rules that said this Lego block and this Lego block and these three Lego blocks and wrap them all in a big distributed transaction and make sure they all work magically and all that sort of stuff. So that's what all that was designed for. And part of the motivation behind this architecture was this idea around shared resources and reusing stuff. And in fact, as an architect in this world, you were meant to look for this particular pattern. So let's say you're a big insurance company, you have all these insurance divisions, and at one point you notice, hey, wait a minute, every one of these divisions has some concept of a customer in it. They're a little bit different because they have different things that they care about customer, but they all have some idea of customer in them. Therefore, what we should do is consolidate all those things together into a single customer service and just let all these divisions talk to that customer service to get all their customer goodies. Seems logical. Two big problems with this. One of which is overcomable but annoying, and the other which is just the death knell of this architecture. The first one is something that Eric Evans talks about in domain-driven design. If you only have one customer service for your entire ecosystem, that thing's going to be really complicated because it has to know everything about everything that ever touches a customer in our ecosystem. So if I'm travel insurance and I have to instantiate one of these things, a lot of details I have to sort through, et cetera, and you can kind of deal with that. This is exactly what Eric Evans is talking about with a bounded context, that every context should have their own implementation, not worry about other people's details because it just gets confusing and it's hard to deal with all those details, but that's survivable. Here's the part that's not survivable. The thing you want to avoid in distributed architectures is brittleness. Brittleness in architecture is when I change some teeny little thing over here and 50 different things and all over the place break. I have a client that I'm working with right now who, for convenience sake, decided we're going to open up some of our table schemas directly to our integration architecture. And so now they are in a situation, it's happened several times now, where a single datum change, you almost never get to use the singular of data, which is datum. A single datum change can wreck their entire system because they change something around that shared field and everything breaks because they've coupled to that tiny, tiny implementation detail. And this is the thing that people don't understand about reuse in software architecture. We codified in our book what we call the first law of software architecture, that everything in software architecture is a trade-off. And a lot of people make mistakes by not realizing that. And this is a great example, reuse. Everybody gets the first part of reuse right and misses the second part. The first part of reuse is abstraction. Hey, look, I can abstract that and use it from a bunch of different places and make it so that I can reuse that thing. That's really cool. That's a great observation. But the second thing to make it useful is low volatility. And that's what killed this architecture. Because now, every time you change that customer service, everything has to stop and coordinate around that change. If you've built an entire architecture around everything as shared as possible, that means every time you change anything shared, even if it doesn't actually affect anybody, everybody has to stop and coordinate around that change. And this is why you shouldn't share domain concepts broadly in an architecture, because what changes the fastest in your software system as you're building it? The domain stuff. That's the stuff you're writing the software about, which is why things that are good reuse candidates are things like frameworks and libraries and plumbing, not domain concepts. Here in this world, if you built everything around these ultimately reusable things, every time you want to change something, everything basically stops. And you have to coordinate around that change and then bootstrap it, and then it changes again and it stops, and it just becomes this impossible situation. That was the death of this. And in fact, that mostly led to the observations in domain-driven design about how keeping implementation details tightly bound is better. You can still pass information, but don't couple to implementation details, because that's what creates this brittleness. And this was a very brittle architecture. The things it was good at, so I've said a lot of bad things about it, the things that we're good at, and this is your new favorite party phrase, protocol agnostic heterogeneous interoperability. That's a fantastic mouthful, isn't it? So what does that mean? Well, interoperability means anything can call anything else. This is an integration architecture world, after all. Heterogeneous means across systems, so it didn't really matter what they were written in. And protocol agnostic means I don't even care what the protocol is. That's the actual benefit of having the enterprise service bus that has the integration hub and the orchestrator and all that stuff in it. You can get by with this. So this is the advantage of this architecture, one of the very few. And in fact, this actually points to the benefit of this architecture, which is contract decoupling. Everything is highly decoupled at the contract level here because you can do these transformations in the enterprise service bus. This architecture is mostly not done anymore, certainly not in this style. For a while there, people were trying to build their entire enterprise ecosystem around this architecture, and it did not go well. This is still used, and it is still useful as an architecture style for what it originally started as, which is integration architecture. A lot of enterprises have old systems that need to integrate with new systems and combine information, et cetera, and that's really the use of that enterprise service bus. So using this as an adjunct to an integration architecture is still a useful thing. But the drivers for this architecture is very much integration, it's on there twice, and orchestration. Now I mentioned in the layered architecture this idea of where does catalog checkout live in the layered architecture? Where does catalog checkout live in this architecture? And the answer is everywhere. It's like you've ground up that domain concept into a fine powder and sprinkled it over the top of this architecture. The real nightmare of this architecture, my microphone just stopped working. Sounded like I think the room mic just stopped working. But I'm pretty loud, so you may not need it. What happened a lot in this architecture is you finally get the thing up and running. It's like, whew, we got it up and running, and then somebody says, oh, we need to add a new address line to the catalog checkout page. It's like, oh man, really? We got to find all the places that dedicated to the catalog checkout page here, and it's scattered all over the place. So yet another reason why this is not a fun thing to do. So this star chart is actually biased against this orchestration-driven SOA because we chose these things because they were desirable characteristics in the current day and age, and none of these things were really even feasible or desirable back in the day. Like agility wasn't a big thing when this architecture was popular. Testability, this architecture was essentially impossible to test unless you're just testing the entire thing all the time. It's anti-simple. It is the most complex architecture. I don't think we'll ever build a more complex architecture because we went down that road and it's like, okay, that just did not work, that level of technical partitioning. And so not a lot of good in this architecture, mostly as a cautionary tale now. Which brings us, of course, to everybody's favorite cool kid architecture, which is microservices. This is the one that has been very popular for quite a while now. In fact, it has now been a decade since Martin Fowler and James Lewis wrote that famous article on Martin Fowler's site. So these architecture styles, it's worth ruminating just for a minute about where these things come from. There really is not an ivory tower somewhere where architects go and scheme to think about what the next big thing is going to be that we're going to impose on the world. Instead, what happens is that, we live in sort of a mushroom forest in terms of capabilities where new things are constantly popping up and new capabilities, and clever architects look at this evolving ecosystem and go, hey, this new thing that just popped up over there, we could take one of those and three of those and wire them together and build this thing that solves this problem we've had forever. We should do that. And when enough architects do that, we eventually say, well, a bunch of people keep doing that. We should give it a name because it's easier than saying 3 of those things plus 3 or 4 of those things wired together. It's just too cumbersome to say. We'll call it microservices. So these are almost always named well after the fact, after a lot of people have been doing them for a while. Microservices is a little bit different because we've gotten more meta about this over time, and we've seen this process play out. And in the relatively early days of microservices, Martin Fowler and James Lewis wrote on Martin Fowler's website this very famous article that still gets thousands of hits a week about microservices. And what they did was talk about this architecture style that a lot of architects were adopting, and very importantly, what it is and what it isn't. And I think that helped a lot, because you're all familiar with the Gartner hype cycle, where things, I'm back, magical. Okay. So the Gartner hype cycle, where things are hyped and then people overuse them and they get abused and they enter into the trough of despair and then it plateaus out and you find good usage for it. I don't think microservices has hit the plateau of despair yet, which means it's still on the uptick, which seems unlikely after 10 years, but I believe what has happened, because we're aware of this phenomenon and aware of the hype cycle, I believe we flattened that trough quite a bit, because we're still seeing a lot of success for people building really highly scalable solutions in this architecture style. We haven't seen a huge backlash against this yet, and it's now been popular for a decade. So, microservices. What's so special about this thing? Well, it's a distributed architecture, meaning that all the pieces are written and deployed as individual pieces, so it's very much designed in pieces, originally as physical machines, and then very quickly virtual machines, and then quickly containers. And then with containers, you get, well, I need these containers to coordinate with each other, so you get orchestration and Kubernetes and that whole ecosystem that we have there. But it's a great example of how evolvable our ecosystem is, that there's not really that much difference between a virtual machine and a container, but that little transition in our ecosystem set off this explosion of stuff. Because as soon as Docker hit our ecosystem, things changed a lot. And now all of our topologies and deployments look a lot different. Those incremental changes lead up to that kind of explosive change that happened. So this is a distributed architecture. And in fact, this architecture is protocol-aware heterogeneous interoperability. So what was the other one? Protocol-agnostic heterogeneous interoperability. So this is one less good, because in the microservices world, you don't want a big giant service bus in the middle doing all this translation for you, because the translation's nice, but the coupling is worse. And that's the philosophy in this architecture, is keep things as decoupled as you possibly can and keep the scope of implementation details as tight as you can. This is, of course, based on the bounded context philosophy from domain-driven design. Each service should encapsulate basically a bounded context. And so even though it would be convenient to have this global translator thing, it would couple all these things together in an undesirable way, and so we don't want to do that. These things are meant to be separately deployed and relatively small compared to other architectures, although the microservice thing has gotten a little bit out of hand. They're really meant to capture a bounded context. Even in the original article that Martin and James wrote, a few of their services are fairly large because it's a bounded context, not as small as you can possibly make them. Service components here are relatively small, but this is actually one of the trickiest things in this architecture. And in fact, this is basically the subject of the entire first half of my book, Software Architecture, The Hard Parts. The first half of that book deals with granularity and structural coupling, and the second half deals with how do these things call each other. And this is surprisingly tricky because, well, what's the right size for my service? Well, it should be single purpose. Okay, now we can have a grand philosophical discussion about how singular is single. Are all customer messages, are all messages singular? Or is it all customer messages are singular? Or each type of customer message, is that singular? Because you can make an argument for all of those, and so this is a tricky thing. So what we did in the Hard Parts book was come up with these forces that we call disintegrators and integrators. Disintegrators are things that encourage you to break them down smaller, and then integrators are things that encourage you to bundle them back together because you've broken them down too small. One of the common problems in this architecture is you follow your instinct as a developer and you break things down really too small. But now you've got to make these things do useful work. And now the data is all isolated. And so now you're starting to pass a lot of data around at the network level, and you realize that, hey, network calls take an order of magnitude longer than method calls. So the stuff we used to do in a single method call is now going over REST, and it takes a lot longer, and all these things are talking to one another, and now all of a sudden my performance is really bad, so you've gone too far. An integrator is something that encourages you to bundle things back together. So I'll show you a few of these here. A common disintegrator is a purpose. Look at the purpose of the thing and break it down in smaller and smaller pieces. But a common integrator are transactions. Because one of the things you want to try to avoid as much as possible in this architecture are distributed transactions. It's the worst kind of coupling you can have. In fact, don't believe me, we actually, in our research for the hard parts book, we found a book from 1993 called What Every Developer Should Know About Object-Oriented Design, which is a really interesting book. He's the one who invented the term connaissance. So if you've never heard of connaissance, that's your homework. Go look up connaissance, C-O-N-N-A-S-C-E-N-C-E, I think, or S-E, connaissance. It's basically the way it sounds. He created the idea of connaissance, but he identified the fact that in a distributed architecture, trying to maintain transactionality across services is the worst kind of coupling you can possibly have in a distributed architecture. So we confirm that. And so, but one of the common ways to avoid that is bundle it back together into a single service, and now the transactional boundary is the service. Sometimes you can't do that because you want scalability, which is in the disintegrator. So what we've basically tried to give you are tools that you can use to iterate on the design of your services, because no one's smart enough to just look at a problem and the exact right granularity of services comes out. So you create a candidate and then you iterate on that design. What if we change this? What trade-offs does that create? Okay, well, let's change this and see what trade-offs. And so that's basically the way to arrive at a good compromise set of trade-offs. This is an observation that Martin and James made, is that microservice is a label, not a description. It's not a commandment to try to make these things arbitrarily small. So this is what I was talking about before. You want to avoid transactions as much as possible. If you have to, there are a bunch of Saga patterns that work in this world, but they're considered a last resort. This is all, of course, because of this idea of bounded context from the domain-driven design world. And in fact, the unique feature of this architecture is data fidelity. One of the great insights that domain-driven design had was implementation details include things like database schemas as well as code. That should be in your bounded context, and none of those details should ever leak out. So you never let one of these things talk to the database of another one. It's okay to put messages back and forth between them, but you want to keep the implementation details internal so that you don't get that rippling side effect of breakage. You can do data replication and caching and other things to be able to make things viewable versus updatable, which is pretty common in this architecture. But that really drives a lot of the decisions in the architecture. You've always heard the adage that the answer to every question in software architecture is it depends. And here's a great example of that. I have some shared functionality that all of my services need. Should I put that in a shared library, let all the services share that same library, or should I duplicate that code in each individual service? Good answer. But what you have to do as a software architect is answer the follow-up question, depends on what? This is one of those questions where, first of all, there is no best practice here. So think about the concept of a best practice for a moment. There are no best practices in software architecture. Because a best practice means every time this situation comes up, I always do this thing. Because it's the best practice. It's not even a better practice, it's the best practice. They're not giving you any wiggle room here by calling it better practice. It's the best practice. And you can just turn your brain off and do that. But you can never do that in software architecture. You always have to evaluate trade-offs because both options suck. Now the question is, which one sucks less? That's your job as a software architect, is not what's the best design, it's what's the least worst design. Because everything has trade-offs. And so the shared question, if I'm in microservices, the correct answer is probably duplication. If I'm in a service-based architecture or monolith, the correct answer is probably coupling. But neither of them are perfect, and you can never answer that question once and for all. You've always got to do the trade-off analysis for the situation you're in, which is what makes it uniquely software architecture and not something you can just turn your brain off for. You often see these things written with an API layer. That API layer is optional, and it is not meant to be a mediator or service bus or anything like that, because all behavior in this architecture is supposed to be inside those bounded contexts. And so that API layer is just used as a facade or as a place for service mesh or some sort of orthogonal coupling like that. As I mentioned before, very often one of the challenges in this architecture is slowness. Poor performance, really good scalability, but lackluster performance. And so that's why events are used a lot in this architecture, asynchronous events. Because when you think about most architectures, when you think about that request-response cycle, request, waiting, response. Okay, I can do something with it. Most of the time in your architecture is waiting for requests to turn into responses when you're using synchronous communication. If you really want to improve responsiveness, go asynchronous so that while you're waiting, you can do other stuff. There are two things in software architecture. We always call it performance, but it's really responsiveness. Because making performance better is really hard, because you've got to change the fundamentals of the thing to make it more performant. But making responsiveness better, you can awfully use concurrency or asynchronous communication and make it look like it's more performant because it's just more responsive. So this architecture has a very specific kind of modularity driven by domain-driven design. It supports agility better than any other architecture because that low level of coupling means I can make changes to these things, test them in isolation, and put them live, usually in an automated way, because this architecture came out after all the modern DevOps practices and continuous deployment, continuous delivery, etc. Really good at these operational things like fault tolerance, but here's the real champion is scalability. Really, some of the most scalable systems written on planet Earth so far have been written in this architecture style. So it has proved that you can build highly scalable things here by spinning up multiple instances of services and spreading out requests along the services. It's very testable because it grew up after the DevOps revolution, highly deployable and automatable, and it is the most evolutionary architecture because it has such a low degree of coupling. And as you see, it scores really well on a lot of our star ratings here. A lot of these are sort of biased toward microservices, but a lot of these things are things that we value in architectures now, and so it's not surprising that microservices are pretty popular right now. So I want to talk about one last thing. We've been talking about architecture styles up till now. I want to give you an example of a couple of patterns. And these patterns can be used, these are communication patterns that can be used in any of the distributed architectures. So this can be used in microservices, it can be used in event-driven architecture, it can be used in service-based architecture. So let's talk about orchestration versus choreography and what some of the trade-offs are and when you might use one versus the other. Because this is another one of those places. I heard somebody just the other day give the terrible advice, oh, you should always use choreography in microservices. So it was a dead giveaway that it was bad advice because it had to do with software architecture and it had the word always in the same sentence, and that's never a good thing. So there are two fundamental patterns that we talk about when we talk about messaging in distributed architectures, orchestration and choreography. And orchestration is named metaphorically for the distinguishing factor of an orchestra, which has a coordinator. Each of these things does a simple thing, and the coordinator manages all those things. So if you've ever looked at an orchestral score, for example, for cello, their orchestral score is something like whoomp, 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 boom, boom. But then you put it all together and it's these magnificent chords. This is a little bit of music trivia, but you know the baton the conductor uses, they didn't always have conductors in orchestras. When the orchestra got big enough, they needed somebody to keep time for the orchestra, and so one of the first conductors of the orchestra used a big stick, and he would thump it on the ground to keep time, which would be really distracting, I think, but that was what they did, until one day he was thumping it on the ground, and he hit his toe, and broke his toe, and it became gangrenous, and it killed him. And future conductors said, maybe not the big heavy wooden stick. Let's use the little light stick, which is a lot less dangerous because, you know, it might poke somebody's eye out, but you'll definitely not break your toe and get gangrene if you have one of those. So a bit of orchestral trivia for you. Choreography, of course, is named after dancers. And the metaphor is really good here because notice the dance is planned beforehand, but no one is directly coordinating that as the dance is happening as you have in the orchestration. So let's talk about which one of these should you use and why. What are the trade-offs between these things? And when you look at these things and do trade-off analysis, it's important to look at the standard happy path, but also look at error and boundary conditions because a lot of times those are interesting, and state management is also pretty interesting. So let's look at orchestration first. And so this is in a microservices architecture. Orchestration is okay, but you never have a global orchestrator. One of the few times I'll say something about architecture and use the word never. At the same time, if you're going to have orchestration, you orchestrate per workflow. So you have lots of little orchestrators, never one big giant one. Because one big giant one ends up coupling everything to everything else, and that is counter to the philosophy of this architecture. You don't want that level of coupling at the global architecture level. And typically this orchestrator can be the state owner, and all it typically owns the state of is the workflow. So the domain behavior is all in these individual services along with their data, and it's managing the state of the workflow. So a request comes in to place an order for a book or something like that, and so my orchestrator can do its job and orchestrate this, send a message to the order placement service, and that'll change its state to I'm in a created state. And then I can tell my customer, yes, congratulations, your order's been placed, your book is on its way. Now I can go to the payment service and say, would you pay for that for me? And now I can change my state to payment applied. Notice that the solid lines here indicate synchronous and the dotted lines indicate asynchronous. Lots of options here to swap those for one thing versus the other. So this is one way to solve this, not the only way by any stretch. So now I can tell fulfillment service, would you ship the order for me, please? There's the order ship state. And now I can send an email to them to say, okay, congratulations, your book is on your way. So let's talk about error handling here and what happens if the payment is rejected. Well, if payment is rejected, now I'm in a different state for payment rejected, and now I have to send a different error message from the orchestrator to the email and say, hey, I'm sorry, the credit card's expired, would you update it, etc. What the problem is. What about back order? Okay, I'm in payment accepted, so I've already applied the payment, but when I go to try to place the order for the thing, it's back ordered, so I can't. And so now I have to go and email them, say, sorry, it's back ordered, but now I have to go back to the payment service as well and refund their order for them. Notice that for the happy path and both of the error conditions I looked for, I didn't have to add any more communication paths. The communication paths I needed were already there. I just reused paths that were already established. So no new architecture to handle those things. As you'll see, that'll come in important in just a second. And that is my state owner, which is that orchestrator. So let's look at what this would be like with choreography. No orchestrator, we'll just let the domain services manage this. So place an order into the order placement service, which will update itself for order placement and send a message back saying, okay, your order is placed. And now this is almost always going to be asynchronous in a choreography because choreography and asynchronous very often go together, although it doesn't have to, but it's quite common. So I'll send a message over to payment service, order paid. It'll chain over to fulfillment service. And then it'll go to email and send an email to the customer, and we're done. wow, that's fantastic. That looks awesome. This is great. This is so simple and nice and clean. It's wonderful. Except, what about payment rejected? Well, first of all, notice that these domain services can't be as dumb as the orchestrated ones. I have to know who the next one in the workflow is, because I have to send a message to the next one in the chain. So these have to be a lot more aware of each other, which complicates things if these domain services need to cooperate in several different workflows. I have to know about the context of every workflow they're in. In this workflow, if this happens, I need to go over here and do this, etc. So payment rejected, because my credit card was expired, now I've got to do an email sent message rather than order fulfillment. What about back order? So I paid the order, I've got fulfillment, but now I'm in back order. Now, back order fulfillment needs to know about payment, because now I need to send a message back to payment and say, hey, by the way, we couldn't fulfill this order. Would you refund this payment? And send an email over to the email service, which is bad enough. But then you get this phone call. Hey, I ordered a book from your website 2 weeks ago. Nothing's happened. What's the state of that order? That's a really good question. I don't know. Where is the state owner of this workflow? It's sort of an aggregate across all these services. One of these dropped a message somewhere or is in an invalid state that didn't get picked up, and it's easy for things to kind of fall through the cracks here. So one of the things you may do here, well, we got additional communication points, but one of the things you may do here is say, well, let's let the first service that we call be the state owner. But if I do that, then that just makes all the extra communication that much worse, because all of these things have to communicate back to that guy to update the state to make it queryable when problems come up. This is so common, in fact, it has a name. This is called the front controller pattern or the front orchestrator pattern. This is where you're basically cheating in choreography and turning the first one into an orchestrator with state about the workflow, because it needs to be somewhere and you need to query it somewhere. And this is the point about orchestration versus choreography. Choreography works great when you have really simple workflows, but the more complicated your workflow is, the more error state, that complexity doesn't just magically go away. So one of the things that we talk about in our book is semantic versus implementation coupling. The workflow I just described here about ordering a book with order placement and payment and fulfillment, etc., that is the semantic coupling of this workflow. The implementation coupling is either orchestration or choreography. Nothing I can do from an implementation standpoint will make semantic coupling less, but it might make it worse. In other words, you can't choose an architecture and make a complicated problem simpler. You've got to deal with the semantics of that problem. And then the question becomes, well, how do you deal with the semantics of that problem? And in choreography, of course, if you have really simple problems, it's easy. But notice, all the communication points we had in orchestration came back one at a time here. But all these things are a lot more complicated because they have to understand the state and of what's going on within that workflow. And of course, nothing is ever homogeneous in this world, so you commonly see hybrid solutions like this. Why not have the order placement service basically interact with my customer, and then have an order placement orchestrator that handles all this asynchronously in the background? And it's like my order placement service own the state of the order, because that's really where the state of the order lives, and then let the orchestrator deal with the error handling and the boundary conditions and all that other stuff and report back to the order placement service when it needs to. So, when should you use choreography versus orchestration? Use choreography, you get better responsiveness, more performance, and better scalability. So scalability is your number one concern. Choreography is great. No bottlenecks. Much easier to do highly reactive architectures where each one of these choreographed services is basically waiting for events. As soon as the event comes, it fires it to another one and gets picked up, and so you can create a very organic kind of workflow like that. And I have less coupling here because we have more contextual coupling, but there's less overall coupling because there's no orchestrator here. Orchestration's better if you have a centralized workflow or if you have something that has a lot of error conditions, boundary conditions, stuff like that. There's a strong correlation between how complicated your workflow is and how useful an orchestrator is. And this is funny. One of the common tropes that we do when we're teaching a class, particularly when we're talking about software architecture, the hard parts, is that architecture is the stuff that you can't Google. Because if you ask Google, should I use orchestration or choreography for my accounting workflow? Google will come back and say, I don't know. But we're not living in the world of Google anymore. We're living in the world of ChatGPT. So I asked ChatGPT that exact question. Should I use orchestration or choreography for my accounting workflow? And ChatGPT came back with about 3 paragraphs of stuff, a general kind of description of choreography and orchestration, and came back with a solution that sounded fairly plausible but was completely and utterly wrong. One of the things they did say, though, at the very end, was that if you have complex workflows, consider using an orchestrator because all that complexity has to go somewhere. So even ChatGPT knows that you should use an orchestrator if you have complicated workflows in your ecosystem. ChatGPT is great if you need knowledge but not wisdom. So that's what it's useful for, is knowledge and not wisdom. So to wrap this up, for architecture styles, the real choice about picking one of these things, none of these are ever implemented in their pure form. They're starting points for implementing some solution. And you can implement almost any solution in any style. The question just becomes, how difficult is it to implement in that style? So what you're looking for is the style that most closely matches the kind of forces you're going to have to be dealing with. And understanding that philosophy allows you to bend it without breaking it. So for example, in microservices, saying, well, I'm going to create one big data service and let every time I need data go through this service, that's breaking microservices in a really bad way. You shouldn't do that if you're choosing an architectural style because you won't end up with microservices. You'll end up with a big mess that looks vaguely like microservices, but none of the good parts of it. A very fancy term that Mark and I use is domain architecture isomorphism. An isomorphism is a one-to-one mapping in mathematics, and that's what you're really looking for when you look at the architecture characteristics analysis, when you look at the domain. Look at the shape of your architecture and what kinds of things you need to support. That will lead you to an appropriate style as a starting point for your architecture. And then, of course, choosing the appropriate patterns for communication, etc. There's a giant catalog of those, many more of those than there are styles. There are hundreds of styles. There are tens of thousands of patterns. If you're curious about patterns and communication patterns, I'll give you 2 great resources. One of them is the website, developer2architect.com. That's my co-author Mark Richards' site. And if you don't know about this, this is a gold mine because there's a link there called Lessons. One of the things that Mark has been doing every other Monday for 4 years now is producing a little 5 to 10 minute architecture lesson called Software Architecture Monday. I take partial credit for the presence of these videos, even though I have not lifted a single finger in helping him create these videos, because in the early days when Mark said, I'm going to start recording videos and releasing them every couple of weeks, I told him, there's no way you'll ever be able to keep that up. And to spite me, he's been doing it for 4+ years now. You have to understand how Mark works, and this is a little Mark anecdote. Mark hates to be told no about something. And so at one point, he had an iPhone 7, and he went to the Apple Genius and said, I want an iPhone 8, but I want the old operating system on it. And the genius told him, no, you can't do that. And that just triggered Mark. And so he kept that iPhone 7 for 5 more years to spite someone whose name he did not even know. And it got to the point where it's like, Mark, you need to get this app. He's like, I'm sorry, I can't because my phone's too. It's like, what are you doing? You're making yourself miserable to spite. So when you understand how Mark works, all you have to do is about every 6 months, I'll say, yeah, you're never going to keep making those videos. And they keep coming. So we'll keep them coming forever. I'll keep pushing that button that's centered on the part of his forehead. The other great resource for communication patterns is the Martin Fowler website. My colleague, Unmesh Joshi, has been writing this really extensive catalog of event patterns with full implementations in Java. He is adamant about getting working implementations of Java in every single one of these patterns. He has hundreds of them now. They're all published on Martin Fowler's website, and he's in the process of consolidating those things into a book now. So he's going to come out with this fantastic catalog of communication patterns for distributed architectures for things like timing, synchronizing timing across multiple distributed systems, and there are a whole lot of very interesting patterns there. As I talk about these things being sort of pure architectures, hybrids are more common than the pure ones. And it's also really important to distinguish patterns from tools and distinguish architecture from implementation. Particularly tools will try to convince you that they are one in everything, understand what architectural problem they're solving before you get too enamored with a particular tool. So understanding what it does is really important. That's it. I'll wrap things up. I'll be happy to answer any questions for you, but thanks very much for having me and hope you enjoyed it. So, questions? Yes?
In your star rating, you have a term for quanta. What does that mean?
The quanta is, so that's our term for a single quantum is a single monolithic architecture, and multiple quanta is a distributed architecture. This is a technical term that we define that defines how the extent of coupling within a distributed architecture. So that's the shorthand for what that means. A single quantum is a monolithic architecture, typically deploys a single project with a single relational database, whereas multiple quantum mean a distributed architecture with more than one data source and built-in pieces. Yes?
You mentioned that the trade-off between using a service or using a shared library. Mm-hmm. Can you give an example of when a shared library is a good idea? And I'm not like trying to argue, just like in my experience, that's like always just been like a bucket of pain.
Yep. This is literally one of our trade-off examples in Software Architecture, the Hard Part. In our last chapter, we talk about this. So what was when a shared library is good or not good? Because I can do both of them. So when is it good? It's really great because you get compile time bindings for it, so you can always make sure that by the time it's running, it's good. You never have to worry about contract versioning. If you're running a service, you may have to worry about contract versioning if one of these changes and the other one doesn't, so you have to worry about versioning at runtime. So those are two advantages. It's also more performant because I'm not making a service call. It's all bound in at compile time, so it's much more performant if it's a shared library. So.
What's like a real world example? Do you have a real world example of when this actually worked and wasn't awful?
Oh yeah, sure. The common example here is the sidecars and service meshes. That sidecar component is often a shared component that you compile time bind into each service, and it manages communication with the service mesh and all that other stuff. In fact, there's a really slick thing that just came out called EBT. I think it's called EBT. That allows you to take your sidecar for service mesh and compile it into the kernel of your container, which means super fast. So forget about just regular process calls. We're talking about kernel level calls for things like logging and monitoring. The problem with that is it has to be really small because you're compiling into the kernel. And there was some dispute. The really tricky thing is HTTPS resolution because that takes a fair amount of oomph to do that. And they were working, last time I looked in on it, they were working on getting enough horsepower to actually do HTTPS resolution in the kernel of your container, which would be super, super fast. But that's an even more extreme example of compile time binding. Yep.
Yes, I was going to ask you, I've seen some systems that have like a process engine and then there's like content created that's like some kind of business processes of maybe a certain type that runs in that engine. Is that a type of microkernel architecture or is it like a flavor of it or is it something completely?
It's definitely a flavor. It may be a complete microkernel. The question is, does that engine do anything at all if nothing's plugged into it? Then it's a pure microkernel. So absolutely. Like I say, once you start seeing this thing, you see it everywhere. So, yep, that's a good example of one. In fact.
Hey, Neal, I have a question.
Yes.
Speaking of microkernels, remember back in the no-fluff days, there was someone on the no-fluff circuit who was always talking about microkernels, and I can't remember what that software was that they were using. Do you remember?
Well, OSGI used to be the thing.
Not OSGI, something a bit more modern than that.
I don't know.
It was like a microkernel like architecture. Anyway, doesn't matter.
Yeah, no.
No, it wasn't JBoss. It was some
Yeah.
very bespoke piece of software, frameworky type of thing.
Yeah.
Anyways. More questions? Oh.
Hey, so do you think event sourcing is an iteration above the choreography or it goes in line with the choreography?
It's a pattern. It could be either one. You could use event sourcing with either orchestration or choreography. Event sourcing is really more about data than it is about communication. So event sourcing is capturing the data stream versus snapshots in data. The classic example of the benefit of event sourcing is, let's say you're doing event sourcing for a shopping cart and they put in a pizza and a Coke and an ice cream, then take the ice cream out and place the order. If you're just capturing a snapshot in the database, you've missed an opportunity to dangle a coupon in front of them next time they show up because you know they're tempted by ice cream, so why not just lean into it? So you get a richer information stream if you can see everything that happens in the event stream. The big problem you run into with event stream when people get super excited with that is you end up getting swamped. So you end up littered with too many events that you can handle, and you got to start dealing with some infrastructure problems around too many events. But that's a really common family of communication patterns in distributed architectures in particular.
Just one last question.
Yep.
On the orchestrator pattern, do you think something like a JBPM or a BPM engine itself can be put in as an orchestrator up there in the pattern?
It can be if you want to live a miserable life and deal with the horrible, horrible side effects and consequences for the rest of your days.
So what else would you put up there? Like what would be the stack?
Well, but so the fundamental problem is that BPM is now coupled to everything in your architecture. So now it's hard to build independent scalability with your services because it's got to scale the same level the BPM tool scales. The BPM's the versioning, contracts, too much coupling. You're much better off isolating. The lessons from domain-driven design and microservices is don't create global coupling in architecture. The more you couple things to mechanisms like that, the more that mechanism becomes the center of your architecture. Microservices would say, forget about that BPM engine, do it inside a bounded context. So domain sharding is a much better way to do that. So a good example of that is I was brought this problem where it's a big, giant credit card processing. We've got to process all these credit cards, and every branded credit card had their own loyalty rules. So they were trying to build this giant rules engine thing that knows everything about it and take every message and try to apply all this stuff. And it's like the transactionality of the system is insane. And then I said, well, how many possible credit cards could there be for a single vendor? And we looked at it, and that was within the bounds of a microservice. And so now every microservice instance or group of service instances owns one vendor's credit card. All the customization rules live there. No workflow engine. Every individual microservice. So that's domain sharding. Sharding around the domain, not around the workflow. That's a much better way to solve that problem because now you isolate the coupling at the service level and no transactions at the architectural level. Everything happens inside the service boundary. So that's the better solution to that problem.
More questions? Anybody? Okay. So while I'm walking back there, Neal, you're going to think this is insane, but 20 years ago, I built an event streaming architecture based on SMTP and IMAP.
Ooh. Well, did you actually use bear skins and stone knives to build that architecture?
I did say 20 years ago.
Hey, so at the very least, it feels like there's been a lot of evolution of like data architectures recently with like data lakes, lake houses. I think I read about like data mesh not too long ago. To what extent do you think that that affects the evolution of like more traditional like application architectures?
So about, I don't know, 5 or 6 years ago, architects finally got it through their thick heads that there are actually two kinds of data in the world. There's operational data and there's analytical data. And we've only really started embracing that idea. So there have been a bunch of swings at trying to solve this really nasty problem. Data warehouse was the first database server that was so big it needed robot arms to swap out, hot swap hard drives. Was in a data warehouse kind of situation. But when you think about a data warehouse, in hindsight, it's the dumbest idea possible. Because what you're supposed to do in a data warehouse is take the operational database schemas and push them through this sausage factory and transform them into this whole other star schema thing on the other side. Okay, it sounds like a cool thing, and you finally get the thing to work. It's like, whew, wow, that was amazing. And then you change one schema in the operational world, guess what happens? The whole sausage factory is broken. You've coupled the implementation details at the finest grain detail across the entirety of the architecture. No wonder it was such a nightmare to deal with. So as many things happen in our world, the pendulum swung completely to the other side. Way too much pre-processing, way too much work, forget all that. We'll just take all the data and dump it into a lake. And we'll figure out, as we need it, we'll do transformations and other stuff for it. Problem with that, though, several problems. One is you have all this great domain knowledge that you have, and then you just throw it all the way into the lake. And then whoever's trying to build analytics has to recreate all that domain knowledge, which is bad. Very often the data lake becomes a data swamp and then a data sewer because it has really poor data quality and nobody's paying attention to it, and it just kind of becomes the repository for let's just dump stuff into it. But the big problem, the thing that's finally pushing people away from it, is PII, personalized identifiable information. Places like GDPR don't play around with that. You can't have solutions where you can invade privacy and that kind of stuff. And if you're working in Europe, you're working everywhere. That's where the data mesh thing is really, really fascinating, because what the data mesh is, was created by my former colleague Zhamak Delhagani. And this is what happens. This is a really useful thing. This is what happens when you take an expert in distributed architectures and plunk her down in front of a really difficult analytics problem and say, think about this really hard for a while. And what came out the other side of that was data mesh. So data mesh is kind of like a service mesh. So let's talk for a second about service mesh. So as I mentioned before, in microservices, duplication is better than coupling, except when it's not. So I don't want to couple my domain concepts together because that's bad. But things like monitoring, logging, authentication, authorization, all the plumbing, I really want those to be consistent and coupled. So that's where service mesh comes in. Sidecar component with all those common behaviors, that creates a service mesh. So you have the sidecar component that's in process for each service, and that solves that orthogonal coupling. So service mesh is really a way to do orthogonal coupling across a distributed architecture. We thought about doing the same for data mesh, but you can't. Because if you have a component, that component, if it's acting on behalf of the analytics world, it may need to do queries into the operational data, and now you've thrown your SLOs for your service out the window. So there's this concept in data mesh of a cooperative quantum. So you have a service, and you have this data product that sits alongside it that's highly coupled to it, but talks asynchronously to it, and it collaborates with the analytical architecture. So you've almost overlaid two architectures on top of one another, the operational architecture, which are services, and the analytic stuff, which is machine learning and business process analysis, et cetera, and they are loosely coupled at the service level with asynchronous communication. Very often that data product has its own database because analytics may not want the direct operational data, it may want a snapshot, an aggregation, and so that's where all that stuff lives. And it's really a cool idea for a couple of reasons. One, it solves this data problem, the analytics and operational problem, in a way that's the best that we've seen so far, because it preserves domain behavior. Everything stays at the service level, the data product. We have PII and other stuff can be dealt with independently, and that's really nice. But the other thing that's really cool about it is it shows us a way of building these kind of overlaid architectures on top of one another as long as we're very careful about loose coupling points. Because data mesh may just be one of the things that we build that sits on top of. So I can imagine an AI mesh where you have something like ChatGPT that runs and analyzes your services in an asynchronous way or looks at analytics or that. So this is really a kind of a gateway to building distributed architectures with orthogonal concerns without creating bad coupling points. So that's why I think it's a really interesting solution, because it's the best solution we've seen to the analytics problem, but it's also a great kind of general purpose architectural solution as well.
All right, Jim. Question from out in left field, since you mentioned ChatGPT.
Yes.
Are we all going to be looking for new jobs not in the tech world a year from now?
So here's my analogy. So we literally just this last week did our ThoughtWorks Technology Radar meeting to put together the next edition of the Radar. Huge number of conversations about ChatGPT, and one of the themes on the next Radar is going to be in fact, the name of the theme is called The Meteoric Rise of Practical AI. But the interesting thing about ChatGPT, so here I'm going to try out my current analogy that I've just come up with on you and see how well you like this. So in the let's say 1971, what did accountants spend 40 to 50% of their time doing? Using adding machines to recalculate spreadsheets by hand. When VisiCalc came out, it literally was a piece of software that accountants walked into the store and said, I want VisiCalc and the computer that it runs on. They didn't know the name of the computer. They knew the name of the software because they could see. That is half of my day is spent recalculating complex, and this just does it magically. This is what ChatGPT is going to be for us. It's the spreadsheet analogy. It's the busy work that requires knowledge but not wisdom. Configuring Kubernetes requires knowledge. Knowing to use Kubernetes requires wisdom. ChatGPT doesn't know about wisdom, but it can sure configure Kubernetes for you. So busy work is going to fall to these smart AIs really fast. Some of you may have used Copilot to do some coding for you. We've done some experience with ChatGPT. It produces like sophomore level code now when you ask it problems. That'll get better over time. But forget about typing boilerplate code ever again. Just like accountants, don't take a big giant paper spreadsheet and for nostalgia's sake, go through it on an adding machine. Boilerplate code is going to go away, but this is great because this is going to allow us to spend less time in wasteful boilerplate things and more time thinking. You know, part of the selling point for COBOL was that finally we can get rid of the pesky programmers and let the business people just write the code directly. And all it did was create more work for us. And that's exactly what assisted AI is going to be. It's going to become a really important tool in your toolbox, but it's not going to replace anybody except really grunt level work.
Well, we were able to get rid of all the accountants after VisiCalc came out, right?
But then you created quants, and then you took accounting to the next level and broke the economy with accounting. So. But it is going to get rid of a lot of grunt level work.
We'll take one more quick question right over here, and we do have to wind up right here. Yeah.
Yeah, I mean, you wrote several books, and I still have O'Reilly subscription, and I love your SuperStream and all. So I see the evolution from books to videos, YouTube, Udemy, with AI and stuff. I mean, is your mode of writing books going to change, or books is going to be forever?
Well, so writing books is interesting. So I'm very purposely multimodal because I hate watching videos to get instruction, but I know a lot of people do. I much prefer reading books. But I try to be as multimodal as possible. The thing I've discovered is it's virtually impossible to get anybody to read a book in 2023 anyway. And so, you know, it's almost a kind of an esoteric exercise anyway to write a book. But I've done it a bunch and I'm good at it and I like doing it because the reason books are still valuable is that it requires a much deeper level of thought and analysis, and the things that you put together can be much deeper and richer than anything you can put on a video or any short form thing. But social media and TikTok have absolutely melted people's attention span. So getting anybody to sit down and read a book is almost impossible anymore. So.
Problem is, like, you can take a paragraph from book and put it in a ChatGPT and ask it to summarize, and it can mean something totally different, and
Well, and it'll come back and it'll sound plausible and it'll be incorrect in subtle ways. Remember, ChatGPT is not a knowledge graph, it's a language graph. So it's going to give you answers that are statistically likely not correct. So ask yourself, how much information on the internet is actually statistically correct? Ooh, that's not a good number. And that's what it's giving you. So there's going to be a lot of misinterpretation of things because of ChatGPT and that kind of stuff. And people just got in trouble. The university just got in trouble for using ChatGPT to write a press release. That's the writing that's going to fall to stuff like this: press releases and announcing DevNexus. Did ChatGPT write the DevNexus copy? That's where it's going to go.
So probably the summarizing question could be like, you don't see a time where you will write articles or something that is catering to an AI model?
Not that I see. I'll tell you what is really interesting are so we talked about a thing on our radar called NanoGPT, which is a self-hosting language model. And you can do stuff like they gave NanoGPT the entire corpus of William Shakespeare and then ask it to compose sonnets in Shakespearean style, and it did a very good job of it. So I think it'd be really interesting to take some of the self-hosting GPT stuff and apply it to really narrow problem domains and then see what kind of synthesis and that kind of stuff you can get out of it. I think there's a whole rich area of exploration that can be done there.
You could probably take the books that you write, or let's say a chapter or whatever, and say, produce a video on this, and there'll be like a
virtual Neal speaking into the camera, right?
Let's hope not. I tell you, I've actually been using DALL-E, the image one, because we're writing a Head First book, and there are artists who do all these highly stylized line drawings. So I need a prototype line drawing of a house with packages stacked in front of it. I could take an hour and create a terrible hand draw, because I can't draw at all, or I can spend 15 seconds and have DALL-E spit out 4 reasonable images. And okay, that's a good prototype. So I've been using it a lot for prototyping images that'll eventually be redrawn by a real artist. So.
As someone who has no artistic ability as well, I totally understand that emotion.
Yep.
So, all right, everybody, thank you for coming. We're going to let Neal go now.